Hello and welcome to our lesson on complex numbers. So complex numbers are going to help us in simplifying radicals that we weren't able to evaluate in our last module. Let me take you back on a little review from maybe your beginning days of your algebra career when you classified numbers. Hopefully this sounds familiar. When you started classifying numbers, you were probably taught that all numbers were real numbers. Okay, every number was a real number, and then the real numbers broke into these two subgroups. Some of the real numbers could be written as fractions, and those were classified as rational numbers, and then some of the real numbers could not be written as fractions. Those would be your non-repeating, non-terminating decimals, and we classified those real numbers as irrational. And then we also said some of the rationals were integers. Those were positive and negative whole numbers. Some of the integers were whole numbers, which would have been 0 and 1 and 2 and 3 and all the whole numbers up to infinity. And then some of the whole numbers were natural numbers, and those would be the counting numbers, so starting at 1, 2, 3, 4, etc. But again, you're kind of taught here that the real numbers are the top of the number classification chart, like the top of the number food chain, when in fact, it's not completely true. Technically, every number is what we call a complex number. So the complex numbers are the top of the number classification, and the complex numbers are composed of two things. There are two components to every complex number. Every complex number has a real number component, and then every complex number also has an imaginary number component. So what we're doing today is we're going to be looking at complex numbers, which means we are combining the reals and the imaginaries. Okay, now I don't know how much experience you have with imaginary numbers, and I would imagine that before combining the two, it would be good for us to talk just about the imaginary. So we're going to start by talking about imaginaries, and then we're going to lump them together with the reals and deal with those complex numbers. Okay, so the imaginary number, which has a variable attached to it. Big surprise, it's the letter I. There are two ways to write the letter I, two acceptable ways. We can write I as a lowercase cursive I, or sometimes you'll see it in text. It looks like a backwards J almost. Those are your two options. But you definitely don't want to do this and dot it or even exaggerate the dot. We definitely don't want to use a capital. Just a lowercase cursive I would be fine for the imaginary number. That's the one I tend to use, but I will sometimes just do that because it's fast. Anyway, the imaginary number is defined for us as the square root of -1. What the heck, right? The square root of -1. And what this allows us to do is it allows us to simplify negative square roots. Okay? It allows us to simplify. Now be careful with language, okay? A real number value is still not going to exist for a negative square root. So for example, if I said to evaluate, that means tell me a real number value for the square root of -25, a real number value for that negative square root still does not exist. There is no real number value for this. So no real number value exists, and in our previous module we would just say this does not exist. Okay, there's no real number value for the square root of -25. Now if I change the direction, instead of asking you to evaluate, if I asked you to simplify, because we've defined the square root of -1 as I, this is something we could do. So remember, let me take you back on a little field trip to the past here. Remember we looked at something like the square root of, let's say, 18. So instead of looking at that as 18, we said, oh, we could make that the square root of 9 times 2. And then we could even separate that as the square root of 9 times the square root of 2. And this would be helpful because we could take the square root of 9, which would be 3. And even though we can't take the square root of 2, we have a simpler form for that radical. So when I showed you how to simplify radicals, I said, well, let's think about this as two separate numbers. Now we also looked at the factor tree, but we know that that made the 3 come out of the radical and the 2 stay in. So we could handle our negative square roots the same way. Instead of thinking about this as the square root of negative 25, we could think about this as 2 separate numbers, right? Negative 1 times 25. And then I could separate that further into 2 radicals, because these are now 2 radicals that I can take. I have defined, well, I haven't defined, but defined for us was the square root of negative 1. We said the square root of negative 1 is going to be I. And the square root of 25 we know is going to be 5. So this is really I times 5. And so we're going to call this 5I. Now if you wanted to make it I5, that's not wrong. It's just a little weird to put a letter in front of a number, so it's a little more acceptable to have it 5I instead of I5. Okay? So that would be the simplified form for that radical. So that direction to simplify is different from evaluate. Okay, there's still no real number value for a negative square root, but the negative 1 under the square root being defined as I allows us to simplify. So in essence, what's going to happen is every time we have a negative under a square root, that negative is going to translate into an imaginary. Okay, otherwise we would break down our square roots or simplify our square roots the same way we did before. So what this allows us to do is take the negative out of the square root as the imaginary number I. Okay, now there's a second definition which will come into play in a few minutes. It is the definition for I squared. Okay, so think about this for a second. I squared, well, we just defined I, right? We said I is the square root of negative 1. So if I took the square root of negative 1 and I squared it, that's what we're saying here. Square the I, square the square root of negative 1. What would happen? Well, the square and the square root would cancel, leaving us just a negative 1. So a second definition is that I squared is equal to negative 1. I squared is equal to negative 1, and that's going to come in handy again in just a little bit. Okay? So let's look at some examples where we simplify some negative square roots. Now, square root of negative 7, if it was a positive 7, I wouldn't be able to break that down, but because it's a negative, I know the negative is going to come out of the radical as an I. So an I comes out of the radical, the 7 is still stuck in there. So just an I and a radical 7. Okay, now 50 I could do a little more with, because 50 is 2 times 25, and 25 is 5 times 5. I could take out a 5. And the negative here is also going to come out. The negative is going to come out as an I, and then the 2 is going to be left as a radicand, okay, stuck inside the radical. So if this was a positive 50, just remember, if this was a positive 50, right, the 2 and 25 would give me a 5 that would come out, and a 2 would stay. This is exactly the same thing, it's just the negative comes out as I. Okay, that's the only difference here. The negative comes out as I. And on this one, you will sometimes see the I written after the radical. It would be totally acceptable to also write, a 5, and then the radical 2, and then the I. I don't like to personally write it that way, because sometimes it looks like the I is in the radical, and sometimes when you're typing it, like using the equation builder in our practices, sometimes that I will get stuck in the radical when it doesn't belong there. So as long as the I is clearly outside of the radical and not under the radical with the 2, it's totally okay to write the I afterward. But just so those mistakes don't happen or misinterpretations don't happen, I tend to stick with the first way that I wrote it, but either one is technically acceptable. Okay? All right, here's one for you to try if you're feeling confident. So we want to approach this the same way we would approach it if it was 6 and positive 40 under the radical. So 40 we would break down to 2 times 20. 20 we know is 2 times 10. And 10 we know is 2 times 5. So we would be able to take out a 2. We would know 6 is already out there, a 2 is coming out, and now because there's a negative, that negative is going to come out as an I. And then left in the radical is a 2 and a 5. So our final simplified answer here is going to be 12i and then radical 10. Okay, or again, 12, radical 10i, same thing. Okay? And moving right along. So here, We got to be careful not to apply a real number property to these negatives under the radical, which are going to end up being imaginary. So it's really easy to say, oh, this is just the square root of negative 12 times negative 3, which would be a positive 36. But again, that multiplying of radicals, that's a real number property that we're not going to be able to apply here. What we want to do is simplify those negatives first. So I'm going to make this an I times a radical 12, right? The negative comes out as an I, and then an I times a radical 3, and now I can multiply. So the I times the I on the outside. Well, I times I, right, anything times itself, we could say is that thing being squared, so we're going to call that I squared on the outside, and then I have a radical 12 times 3 on the inside, which is 36, and since those are positive, those are real number square roots, I can apply that property. Okay? Now, not quite done with this one for two reasons. One, we should know the square root of 36 can be simplified, and I squared we defined earlier. Okay, since I squared is defined, we want to simplify both of these parts. So instead of just an I squared times the radical 36, this becomes, we said I squared is a negative 1, and it's going to be multiplied by the square root of 36, which is 6. So I squared becomes negative 1, square root of 36 becomes 6, and if I multiply negative 1 times 6, that makes the final simplified form of this problem negative 6. So our answer is negative 6. Okay? Crazy, I know. Alright, so one for you to try if you, again, feel good about this. We want to, before we try to divide, I cannot apply that real number property here. I want to simplify that negative. So I'm going to make the numerator here an I and then my radical 18. And then denominator, I'm going to leave that radical 3. Now I can divide this. So an I divided by 1 on the outside here is still going to be I. And then I have a radical 18 divided by 3 is going to be 6. And that's it. I radical 6. Okay? I'm just going to move this down so it get mixed up with my other problem. Okay? So simplifying negatives under the square root, it doesn't change what we were doing before. Break down the radicals if you can. Just make sure those negatives come out as i's, and then we're using the same tools and properties that we've discussed before. Okay? Now that we have a little bit of experience and a little bit of a grasp on what the imaginary number is, we're going to look at our complex numbers, which again is where we combine the reals and the imaginaries. So a complex number has a real, oops, turn the pen on, goofy, has a real number part and an imaginary number part. So we're putting the real and the imaginary together to make this complex number. And we have a standard form for the complex number. So the standard form for a complex number is a plus bi, where a just represents the real number part. So a could be something like, 5 or negative 20 or some real number. And then b times I is our imaginary part. So b is a coefficient. It can be any number in front of the I, but the imaginary here, well, let's lump it together. Okay, that's going to be our imaginary number part. So some coefficient of I. So like this example here, 2 plus 5i, this is the real number part of that, and the 5i is the imaginary number part of that. Now, because addition is technically commutative, it's perfectly acceptable to say 5i plus 2. Those are equivalent, right? They're equivalent. But the standard form says put the real number part first and then the imaginary part. So it's a little more proper to write it as 2 plus 5i. Okay? So we're going to say this is 2 plus 5i. Now, technically, every number is a complex number. 2 plus 5i is very clear because we can see the real number part and we can see the imaginary number part. Now 3 doesn't look like a complex number, but it is. Okay, the complex number, or the part of the complex number we see is the real number part. If we don't see the imaginary part of it, it's because it's 0. So this is technically the same as 3 plus 0 imaginary parts, 0i. And the same thing with 7i. We clearly see the imaginary part there. Technically, the real number part is just 0. So this is the same as 0 plus 7i. Okay, technically every number is a complex number. If we don't see one part of it, it's because it's zeroed out. All right? Now, operations with complex numbers is really the goal for today. So how do we add, subtract, multiply, and divide complex numbers? Fortunately, pretty simple. We're going to be treating our imaginary, like we treat x or any other variable. We saw a snippet of that in the beginning, right? If I multiplied I times I, got I squared, just like multiplying x times x would give us x squared, right? So we're going to treat I like x or any other variable. So for instance, problem number 4 here, if I was going to subtract, we have parentheses to say take this complex number and subtract this other, but all we're going to do is distribute where we can distribute and then combine like terms. It's just that our like terms will be real numbers and our real number parts will go together and then our imaginary parts that go together. Okay? So this would be just like if we had a negative 2 plus 4x and a 6 minus 8i that we were trying to subtract, or 8x that we were trying to subtract. So I can bring these first two terms down without the parentheses, because outside of the parentheses a positive 1 would do nothing there. But be careful on the next set of parentheses, since there's a negative 1 to distribute here, that's going to make that a negative 6, and it's going to make that a positive 8i. And now I combine my like terms. So I'm going to combine my real number parts, the negative 2 and the negative 6, which makes negative 8, and then combine the imaginary parts, positive 4i and positive 8i makes positive 12i. And that would be my complex number result. And again, if you put 12i minus 8, it's not wrong. It's just a little more proper to have it in the standard form where the real number part comes first. So negative 8 plus 12i is it. Okay? Or multiplying, just like distributing a 7x, we can distribute a 7i. So 7i times 1 would be 7i. And then 7i times 4i would be, let's see, 7 times 4 is 28. And I times I would be I squared. We just got to be careful if we see that I squared, because it's defined for us, we want to replace I squared. So anytime we see I squared, we're going to replace it with what it's defined as, which was a negative 1. So this is going to be 7i plus 28 times, instead of I squared, negative 1, which makes it a negative 28. And to make this standard form, we're going to put that negative 28 first, followed by the positive 7i. Okay? And moving right along, 3 minus 9i squared means we have to multiply 3 minus 9i by another 3 minus 9i. And so if we distribute the 3 times 3 is going to be 9. 3 times negative 9i would be negative 27i. We've got the same result here, negative 27i. And then at the end, negative 9i times negative 9i is going to be a positive 81, and then an I squared. Okay, so we can simplify a little here. This 9, let me leave that alone for a second. I know that I can combine these like terms. So 9's going to come down, combine the like terms here. Negative 27i and negative 27i is going to be negative 54i. And then I know I squared is going to get replaced by negative 1, so this is really 81 times a negative 1. So 81 times negative 1 makes that a negative 81, and when I combine that negative 81 and that positive 9, I get a negative 72. So I'm going to have a negative 72 and then my negative 54i, and that would be my complex number result. Okay? And 7 is where it starts to get a little bit interesting. So on 7, we're asked to divide 5 by 2i, but 5 doesn't divide evenly by 2, and we're definitely not going to be able to divide an I in there. It'd be like if I had 5 over 2x. I can't actually do the division. Now 5 over 2x we could leave, but this particular situation we can't leave, and it's similar to a situation we saw in the last module. So if I had something like 5 over 2, let's say radical 3, We didn't want to leave the irrational number in the bottom of the fraction. It's a similar concept here, and it should make sense that it is because I is really just a radical. I don't want to leave the imaginary in the bottom of the fraction in the same way I don't want to leave the radical 3 in the bottom of the fraction. So in this case here, we multiplied by a radical 3 and a radical 3 because that gave us a radical 9, and that perfect root eliminated the radical from the bottom of the fraction. So we multiplied by a form of 1. It's the only thing we can multiply by to not change the value of the fraction. So we're going to do the same, or use the same concept here, where we're going to multiply this fraction by 1. We just want to use a form of 1 that's going to be helpful. Any ideas? Maybe something's happening in your head there? If I multiplied this particular fraction by I over I, and then I'm multiplying by 1, again, not changing the value of the fraction, but what happens on the top? 5 times I is 5i. On the bottom, 2i times I gives us 2i squared, and I squared can be replaced. So this becomes 5i over 2 times negative 1, which means we can make this 5i over a negative 2. And the imaginary in the top of the fraction is acceptable, it's just not something we want to leave in the bottom. So we're going to make this again 5i over negative 2. Now the negative, I don't care if you leave it in the denominator like that, I probably would, but just so you know, it doesn't really matter if it's there. You could also have the negative out in front of the 5i and the 2, or you could also have it on the top, negative 5i over 2 like this. It doesn't really matter where the negative goes, but you should recognize that one negative within that fraction makes that whole thing negative. Okay, so any of those answers would be acceptable. I would probably stick with the first one just because that's what I ended up with. But so you're aware, it doesn't really matter where that negative goes. Okay? All right, so here, any ideas what we do with this guy? Because again, it's asking us to do some subtraction, which we can't do, and division, which we can't do. But again, I don't want to leave that imaginary in the bottom. But this time, the denominator is a binomial. So what are we going to do? Just like in our radical unit, okay? If this is 12 over 1 minus a radical 3, then we would have multiplied by 1 plus radical 3. We would use the conjugate of that denominator because middle terms cancel, right? The same thing is going to apply here. We're going to see how it works out for us in just a second. Let me, real quick, give myself a little bit of space here. If only you could just cheat like that on your paper, huh? Okay, so we're going to multiply by the conjugate of this denominator, and you're going to see why that's so helpful in just a second. The conjugate, remember, same terms, just the opposite sign in the middle. So when we multiply here, 12 times 1 is going to be 12. 12 times 3i is going to give us 36i. On the bottom, which is where it gets a little more interesting, the 1 times the 1 is going to be 1. And the positive 3i that we get here is going to cancel with the negative 3i that we have here. And then the negative 3i times 3i gives us a negative 9i squared. And so 12 plus 36i in our numerator. In our denominator, again, these positive 3i, negative 3i cancel. And I know that this negative 9i squared is really going to be a negative 9 times a negative 1, which makes it a positive 9. So in our denominator, I've got the 1 and the 9, which gives me a 10. Now this fraction has 3 terms, the 12, the 36i, the 10, and they all have a 2 in common, which means I can go one more step here. I can reduce this fraction by dividing it by the 2 that all of the terms have in common. So that's going to leave me with 6 plus 18i all divided by 5. And again, I would be perfectly happy with you leaving the answer there, but recognize that this would be the same thing as 6 over 5 plus 18i over 5, where each of the terms in the numerator can be divided individually by our denominator, and technically you could even see this 18/5 I, the I written after the fraction. That's totally acceptable too. Right, so I'm okay with the first form. You just got to recognize that there are other ways to write these things. Okay? All right, one for you to try. And 9i divided by 10 plus I. So to fix this, to simplify this, we're going to multiply by the conjugate of our 10 plus I, which is going to be 10 minus I. So on the top of the fraction, 9I times 10 is going to be 90I. 9I times a negative I is going to be a negative 9I squared. And then on the bottom, knowing that when you multiply conjugates, the middle terms are going to cancel. If you want to skip that work, that's totally fine. So 10 times 10 is going to give us 100. And I know the negative 10I and positive 10I are going to cancel. So if you wanted to skip that, you could. I just don't want to take any shortcuts here in my notes. And then at the end, I times negative I is going to be a negative I squared. So now we can simplify a whole bunch. We've got 90I, and then this becomes a negative 9 times a negative 1, which again makes this a positive 9. And then on the bottom, we have terms that cancel, and negative times an I squared is a negative times a negative 1, which makes that a positive 1. So we've got the 100 and the positive 1, so 101. And 101, prime number, none of those, the three terms have nothing in common other than 1, so we can leave this. We just want to make sure our numerator's in standard form there, so we're going to go 9 plus 90I all divided by 101. Or again, if you had 9 over 101 separated from 90 over 101I, something like that would totally be fine too. Okay, so there it is. Now, ready for probably the most challenging part of this. So far, this really isn't anything new. Adding, subtracting, multiplying, not a big deal. Using some of the rationalizing techniques, applying it to imaginaries. Again, we've seen that before, but here's where it gets a little more interesting, right? Let's kick it into, what are we at, first, second, third gear now, okay? Let's look at this division problem. Just like if these were x's, we can go ahead and divide 30 by 6 to make 5, and we could subtract those exponents. 7 i's on the top and 3 i's on the bottom are going to reduce out to I to the 4th. However, 5I to the 4th is not something that's defined for us, okay? In our imaginary number side of things, we only have a definition for I, and then we have a definition for I squared, which basically just gets replaced. The only imaginary that's going to be allowed is just I to the 1st. We already know how to replace I squared, but any other higher power of I is going to have to be fixed as well. It's going to have to be simplified as well. So how do we go about simplifying something like I to the 4th? So let me leave the note page for a second here. So we said that I to the 1st was just going to be I, all right? Anything to the 1st power is itself. And we defined I squared as negative 1, and I showed you how the square and the square root would cancel, so negative 1's our definition there. Now what if we had I to the 3rd power? I to the 3rd power, how do we fix that? Well, we can think about I to the 3rd as separate things, okay? I to the 3rd, for example, I could say is, well, obviously I could say it's I times I times I, right? Which isn't really helpful because that's just I to the 3rd again. But if I lumped these two together, so instead of I times I times I, if I said I squared times I, then I'm in good shape because I squared can get replaced with a negative 1, and then we can leave the I to the 1st in there. So it really becomes a negative I to the 1st, okay? Or I to the 4th, for example. I to the 4th, I could say is I squared and I squared, right? There's still 4 i's being multiplied together there, which would be helpful because both of those get replaced with negative 1. And negative 1 times negative 1 becomes a positive 1, all right? Or what about I to the 5th? Okay, lots of different ways I could try to go about this, right? How many I squareds are in there? So this would be I squared, and then one little leftover I. So negative 1 times negative 1 times I, or just an I. And I could keep going. The issue is what happens when this becomes a larger power. So fast forward to like I to the, I don't know, let's say 20th. I don't want to have to rewrite how many I squareds are in there and then figure out what's left over. The shortcut is, if I want to figure out how many I squareds are in I to the 20th, I'm just going to divide 20 by 2. So 20 divided by 2 means, how many I squareds are in there? 20 divided by 2, this should have been in here, is going to be 10. So there are 10 I squareds wrapped up in that I to the 20th. And I squared, again, becomes a negative 1. So now it's negative 1 to the 10th power, and negative 1 to the 10th power is just 1. So I to the 20th, for example, becomes 1. Or let's say it was I to the 21st. Okay, if I wanted to know how many I squareds that was, well, 21 divided by 2 is still 10, but there's going to be 1 left over in that division. So I would still have the negative 1 to the 10th power, but it's multiplied by that leftover I. So 1 times the leftover I would just be an I. Or if it was I to the 22nd, okay, I to the 22nd, how many I squareds is that? Well, 22 divided by 2 is exactly 11. And so this would be a negative 1 to the 11th power. But now because negative 1 is being raised to the 11th power, I get a negative 1 as a result. Or if it was I to the 23rd, then how many I squareds is that? Well, 23 divided by 2 is 11, but there's 1 left over this time. So this would be negative 1 to the 11th times that leftover I. So a negative 1 times the leftover I, which is a negative I. Okay? And then this process would just repeat. So if we have a higher power of I, what we want to do is figure out how many I squareds, how many negative 1s are in there that we could get rid of, and then all we're going to be worried about is what's left over, right? And if we have an even or odd number of I squareds to make either a negative 1 or a positive 1. All right, so here, this 5I to the 4th is going to be 5, and then how many I squareds are in I to the 4th? Well, the 4 divided by 2, if I divide those, then I get a 2 to go here, no remainder. So we're going to make this 5 times I squared gets replaced with negative 1 squared. And that's 5 times 1, which means this simplifies down to 5. Okay, just a 5. And then we could use the same process here. So this is going to be I squared how many times? Well, if I take 43 and divide it by 2, okay, and you don't have to try to do that in your head. 43, if I try to divide it by 2, it's going to go in 21 times, and then there's going to be 1 left over. See the 0.5? That's 1 out of the 2 left over. So 21, if I divide those, I get 21 here, and then there's going to be 1 I left over. So that's 42 plus 1, which makes the 43. Okay? So now we're looking at an I squared gets replaced with negative 1 to the 21st power times I, and that's going to be negative 1 to the 21st power. That's going to be a negative 1 in front of that I, so a negative I. And similar here, okay? So this is going to be 2 times how many I squareds are in 61 I's. So if I divide 61 by 2, that's going to be 30, and then there's going to be an I to the first left over. 30 with the remainder of 1. Okay, there's 60 right here, plus the 1, which is the 61 altogether. Okay, so now I have 2, and then I squared gets replaced with negative 1 to the 30th power times I. Well, negative 1 to the 30th power, since that's an even number of negatives, it's going to be a positive 1. So this is 2 times positive 1 times I, which just makes it positive 2I. Okay, and then one last one here for you to try if you feel like you can do it. How many I squareds are there in 86? Well, if I divide 86 by 2, I get 43. Exactly 43, nothing left over. So this is really negative 1 to the 43rd power, and an odd number of negatives means this is going to stay a negative 1, and no i's, so just a negative 1. Okay? It's probably the hardest part of what we had to do there. If you've got some problems to work on for practice, but if you find yourself struggling and you need some extra help, then by all means, just reach out. I'm here to help. All right, guys, take care.